Konnichiwa, chemistry students of the world. Welcome to Passmark Chemistry, where we help you to pass your chemistry exams. Well, today we're talking all about aldehydes and ketones, and maybe by the end of this video, we're going to figure out which one's best. So the aldehydes and the ketone are two different homologous series. So they have their own functional group and their own pattern of what makes them an aldehyde or a ketone. But what's interesting about these is they're connected through their shared functional group. That C double bond O is its own functional group that they both share, but its position means I have either one or the other. All right, let's do a little bit of background first. If you're doing any organic chemistry, chances are you've heard the terms homologous series before. A homologous series, like a family of organic compounds that are all related. I would say that they're related through the same general formula, similar chemical properties, and a trend in physical properties. And for different homologous series, they have their associated functional group. So my alcohols have a functional group of this OH, which we call the hydroxyl. The series are called the alcohols, but the functional group is hydroxyl. Carboxylic acids have a C double bond OH, which is the carboxyl functional group. And then we have aldehydes and ketones. And these guys share a functional group. C double bond O, a carbonyl or carbonyl. Not sure in the pronunciation, I've heard it either way. Carbonyl sounds nice and Scottish, maybe a small village in the Highlands. The village of Carbonyl. Whereas carbonyl sounds a little bit like an Italian sauce. Let me know in the comments what's your preferred pronunciation. I'm going to stick with carbonyl because I enjoy saying it. So our carbonyl functional group, the C double bond O, is for both of them. So then how can I tell the difference between an aldehyde and a ketone when I see one? Let's take a look. Now I've drawn out an aldehyde and a ketone. Now I know they're an aldehyde and ketone, which one's which, but how would you know which one's which? Well, the way that we work out if you have an aldehyde or a ketone is the position of the carbonyl. Remember our carbonyl, C double bond O. This functional group is called a carbonyl. Carbonyl. So our functional group is linked between the two of them, but the position of it means I have one or the other. If my carbonyl is on the end, one of the end carbons of the molecule, then it's an aldehyde. I call these end carbons terminal carbons. If you've ever had a terminal illness, you're at the end of your life. At the terminal of the airport is the last point before you take off. So the end, the terminal carbons. And on either of the terminal carbons, if you have a carbonyl, you have an aldehyde. For my ketone, on the other hand, my carbonyl is always somewhere in the middle. Now, I've only drawn a very little ketone here with 3 carbons, but it doesn't matter how long it is, as long as it's any one of the middle carbons. Basically, anyone that's not a terminal carbon. As long as it's not on the ends, anywhere in the middle, it's a ketone. So that's how I know if I have an aldehyde or a ketone, the position of the carbonyl. My aldehyde's always on the terminal carbons. My ketone is any of the middle carbons, is where the carbonyl is. Now the next thing is I want to know how to name them. I want to be able to figure out, no matter what structure I've been given, how I know if I've got an aldehyde or a ketone and how I would name that one. Well, hopefully by now we know our at least 1 to 10 in carbon language. Meth, eth, prop, bute, pent, hex, hept, oct, non, dec. So that's our 1 to 10. Hopefully we know it. So if I have 3 carbons like this, well, that's prop. So this is a prop and al. Al like aldehyde. Propanal. Over on this side, I've got my ketone with 1, 2, 3 carbons as well. So I remember that that's prop. It's a propan. And then for a ketone, it's going to end in one. O-N-E. Spelt like one, O-N-E, but ketone, propanone. So an one at the end for ketones, ones. Now these are quite simple examples because they're quite small, but let's take a few trickier examples and see if we can name those. You can pause the video now, try and name this yourself, and then we'll go into working out what this is. So this whole structure here, the first thing I notice is that my carbonyl functional group is right here on a terminal carbon. So I know this is an aldehyde. So if I'm building up the name of this, I'm going to start with the very end of the name. I know it's an al. So it's an aldehyde, it's going to end in al. So my al is right at the end of this name, and then I know I've got 4 carbons. So this is a bute. Bute is 4 carbons. So bute, al. Now, unlike, say, alcohols, for instance, where I need to put the number of which carbon the functional group appears on, I don't need to worry. I don't need to call this a butane 1-al because all aldehydes are going to appear, the functional group, on carbon number 1. That's always where I count. This is carbon number 1 because it's where the functional group appears for an aldehyde. So that's 1, that must be 2, that must be 3, that must be 4. I have to count from the functional group. And because it's always on number 1, I don't need to put number 1 every time I do an aldehyde. So it's just an al. So this is a bute, an al. And don't forget that AN part. The AN is important. The AN lets me know that it's all single carbon-to-carbon bonds. If there was a double bond anywhere, it'd be an EN, butanal. So my butanal, is most of this structure, but I've got an extra branch up here that I didn't count as part of my line of 4. So this is a 1-carbon branch. 1 in carbon language is meth. And because it's a branch, it gets a YL, methyl. So methyl butanal. And the last thing is, I need to put the number on it. And this is really important because usually we would count a branch from the shortest side of where it appears, 1, 2. But what takes precedence over that, or priority, is the fact that the functional group here is number 1. And I have to count from the functional group. So 1, 2, 3 means I have a 3-methyl butanal. I have another structure now. You can go ahead and pause the video, try and name it yourself, and in a second, I'll just tell you how to work out the name. Okay, so this structure here, my carbonyl functional group, is right here in the middle, not at one of the terminal carbons, in the middle, so this is definitely a ketone, so it's going to end in -one. Now, unlike the aldehyde, which is always going to be on number 1, because I've got more options of where that carbonyl can be for a ketone, I do need to put the number on it. So I'm going to go 1, 2, 3, or 1, 2, 3, 4. The shortest end wins, so 3. So my 3-one. And to separate my numbers from my letters, I always do dashes. So 3-one for this ketone. Now, I always work backwards from how I name this. So I've got my functional group, the end of the name. It tells me what homologous series it's in. I know what number of carbon it appears on. 1, 2, 3. I'm going to even mark in those numbers. 1, 2, 3. Because once I start counting from one end, I have to continue to count in this direction. So I've got a line of 6. That's my longest continuous chain. All single bonds, so it's an AN. And 6 in carbon language is hex. So hex and 3-one. A hex and 3-one. But I've got some branches again. I've got a branch right here and a branch right here. So these 2 branches I've got now. But they are both the same thing. They're a 1 carbon and a 1 carbon, so that's both meth. So I know to write a methyl. Only thing is if I've got 2 occurrences of the same thing, it gets this little prefix di. So a dimethyl. Di for 2, tri for 3. So my dimethyl hexan 3-one. Last thing is I need to say what number these 2 branches appear on. Now for this one here, they both appear on carbon number 5, and I do need to say the number twice. 5, 5 dash. To separate numbers from numbers, I use a comma, and to separate numbers from letters, I use a dash. So I do need to say the number twice, and this is a very common mistake students make, is they think, well, they're both on 5, so I'll just say 5 once. But with only one number there. Anyone else reading this might think 5-dimethyl. Oh, the di must be a mistake because there's only one number there. So 5,5-dimethyl means no one's going to make that mistake. On the 5 and on the 5, I have two methyl branches on a line of 6, all single carbon-to-carbon bonds. And then on the third carbon, there's a carbonyl, which makes this a ketone. Now let's take a look at how I would distinguish, if I was in a lab, between an aldehyde and a ketone. Let's say I had sample jars of both, of this propanal and this propanone. They have the same formula though, and maybe these are very old bottles. Maybe the names got worn away, but the formula was still there, C3H6O. But how do I know the difference? They have the same formula, C3H6O is the same for both of them. That would make these isomers. So isomers, same chemical formula, but different structural formula, these two isomers. And yet that different structure means that they are going to react in different ways. One of the ways I would tell the difference between these two is through an oxidation reaction. If I was to oxidize both of these, so I'm going to add some kind of oxidizing agent. A particularly fun one would be something like Tollen's reagent. Tollen's reagent is fun because when it oxidizes is the product that to show that such an oxidation has taken place, you get a silver mirror, which looks pretty cool. And this is how I would distinguish between these two, is if I add my Tollen's reagent, my oxidizing agent, to both of them, only one of them is going to oxidize. Now remember, in organic chemistry, our definition of what an oxidation is that it forms more bonds with oxygen and less with hydrogen. More bonds with oxygen, less with hydrogen. That is our definition. So what would this aldehyde here, this propanal, look like if it had more bonds with oxygen and less with hydrogen? Well, let's try and draw that out. It's going to keep its 3 carbons, but whereas it had 2 bonds with oxygen before, more than 2 is 3. So more bonds with oxygen would give me that double bond that I already had, and then an O here. And of course, oxygen needs 2 bonds, so it's an OH. And I've got myself an acid, a propanoic acid. So my oxidizing agent turned my aldehyde into a carboxylic acid. More bonds with oxygen, less with hydrogen. And less with hydrogen is I had 1 bond with hydrogen, and now I've not got any. So 3 bonds with oxygen. So more bonds with oxygen, less with hydrogen, and the way that this would be observed with the Tollen's reagent is that in my beaker or my test tube, it would go silver. I'd have a silver mirror appear. Now, if I was to apply that same kind of reaction to a ketone, more bonds with oxygen, less with hydrogen, let's see what would happen. Well, I had 2 bonds with oxygen here, so I need 3 bonds with... Can't be done. It's not going to work. I cannot oxidize my ketone because I cannot have more than 4 bonds to carbon. My 4 bonds to carbon is kind of our rule in organic chemistry. Cannot have more than 4 bonds. So it's already got the 2 bonds to oxygen and 2 bonds to either carbon. It's not going to break a link to a carbon. And if the whole point of an oxidation is to have more bonds with oxygen, it's reached its maximum at this point. And this is how I would distinguish between an aldehyde and a ketone in the lab, is that one would oxidize and one would not. So there we have it, our aldehydes and our ketones. We've talked a little bit about how to identify the difference between them, about how to name either one, the sort of reactions that would be used to distinguish one or the other. But there's the last question, which is better? Well, let's weigh up their stats. My ketones, what are they good for? Well, this one, the propanone, sold as acetone in the shops, used for removing nail polish, but it's also pretty good at removing kind of glue or paint, so it's a pretty good cleaning product. But other than that, they're a little bit harder to name because they've got more options. I've got to put a number in it, and they don't oxidize. They don't get any kind of reaction there. Whereas my aldehyde, I never have to worry about the number on where my carbonyl appears. It's always number 1. So that gives me one less job to do. They also oxidize. And if I'm oxidizing with something like Tollens, I get a very cool reaction. So I think we have our winner. Who's better, aldehyde or ketone? Aldehyde. Maybe you disagree with me. Let me know in the comments section below. If you've taken anything from this video, make sure to hit that like button, hit that subscribe button. And if there's any more chemistry videos you'd like to see, then let me know in the comments section below. Okay, thank you for your time, your patience, and your attention. Goodbye.